You've seen it in movies 100 times. Someone opens an airplane door at cruising altitude and chaos erupts. Papers fly, passengers get sucked out, oxygen masks deploy, and the cabin turns into a wind tunnel. It looks dramatic, it looks terrifying, and it's almost completely wrong. The reality of what happens when you try to open a plane door at 35,000 feet is far more interesting than Hollywood suggests. Because here's the thing most people don't realize. You can't open it. Not because it's locked, not because flight attendants are watching, but because the laws of physics make it physically impossible. Let me explain exactly why. First, let's frame the problem. At 35,000 feet, the air pressure inside the cabin is artificially maintained at roughly the equivalent of 6,000 to 8,000 feet elevation. That's comfortable for humans. Outside the aircraft, the pressure is about 1/4 of sea level pressure. That creates a massive pressure differential. The cabin is pressurized to around 11 to 12 psi, pounds per square inch. Outside, it's roughly 4 psi. That difference, around 8 psi, doesn't sound like much until you understand what it means in terms of force. A typical aircraft door is about 6 feet tall and 3 feet wide. That's roughly 2,600 square inches of surface area. Multiply that by the 8 psi pressure difference, and you get over 20,000 pounds of force pressing the door into its frame. That's 10 tons. You're not opening that door. A human can generate maybe 100 to 200 pounds of pulling force. You'd need the strength of 100 people simultaneously pulling to overcome that pressure difference. It's not happening. Now here's the misconception that needs to be destroyed immediately. Movies show doors being ripped open, explosive decompression, and people being violently sucked out. That imagery is based on a fundamental misunderstanding of how aircraft doors work. Commercial airplane doors are not like car doors. They don't swing outward on hinges. They're plug doors. That means before the door can open outward, it must first move inward, then rotate, then push outward. The pressure differential actively prevents that first inward movement. The door is being pressed into its frame with multiple tons of force. It's physically locked in place by air pressure alone, even if every mechanical lock were removed. Let's break down the mechanics. When you look at an aircraft door from inside the cabin, you see a handle and a simple-looking mechanism. But the engineering behind it is anything but simple. The door sits in a frame that's slightly smaller than the door itself. The door frame has a lip that extends inward. When the door is closed, it sits against that lip from the inside. Cabin pressure pushes the door outward against the lip, creating a seal. To open the door, you'd need to pull it inward, past that lip, rotate it, and then push it outward. But the pressure differential makes pulling it inward impossible. This design is intentional. It's called a pressure sealing plug door, and it's one of the most elegant fail-safe systems in aviation. The higher the cabin pressure, the harder it becomes to open the door. The system becomes safer, the more dangerous the environment becomes. That's good engineering. Now let's talk about what would happen if, hypothetically, the door could somehow be opened. Let's say the pressure differential didn't exist, or the aircraft was at low altitude where cabin pressure and outside pressure were roughly equal. What happens then? You'd get rapid decompression, but not the explosive Hollywood version. Real decompression in a commercial aircraft happens over several seconds, not instantaneously. The hole created by an open door is relatively small compared to the cabin volume. Air rushes out, pressure equalizes, and yes, loose objects near the door would be pulled toward the opening. But it's not a violent explosion, it's rapid airflow. Oxygen masks would deploy automatically when cabin pressure drops below a certain threshold, usually around 14,000 feet equivalent altitude. Passengers would experience a loud rushing sound, a temperature drop, and fogging as the cabin air, which contains moisture, rapidly expands and cools. Ears would pop painfully, but the aircraft itself would remain structurally intact. The fuselage is designed to handle decompression events. It's not going to rip apart. Here's a real-world example. In 1988, Aloha Airlines Flight 243 experienced an explosive decompression when a large section of the fuselage roof tore off at 24,000 feet. The aircraft didn't disintegrate. The pilot safely landed it. That was a massive structural failure, far worse than an open door, and the plane still flew. Modern aircraft are built with this kind of redundancy. But let's go deeper into the physics. Why does air rush out when pressure equalizes? It's basic fluid dynamics. Air flows from high pressure to low pressure. Inside the cabin, you have high pressure, outside low pressure. Open a hole, and air molecules move from the high pressure zone to the low pressure zone until equilibrium is reached. The speed of that airflow depends on the size of the hole and the pressure difference. For an open door at 35,000 feet, the initial rush would be violent, but it would slow as pressure equalized. Now here's another critical detail: the temperature. At 35,000 feet, outside air temperature is around -50 to -60 degrees Celsius. If the door were open, that freezing air would flood the cabin. Passengers near the door would experience immediate cold shock. Frostbite would occur within minutes. Hypothermia would follow. But again, this is hypothetical because the door isn't opening in the first place. Let's address the human factor. Could a person be sucked out through an open door? If the door were somehow open during flight, yes, anyone standing directly in front of the opening would be at risk. The airflow would be strong enough to pull them toward the hole. But the word sucked is misleading. Air doesn't suck, it pushes. The higher pressure inside the cabin pushes objects toward the lower pressure outside. It's not suction, it's differential pressure creating a net force. Now, what about at lower altitudes? If the aircraft were at 10,000 feet, the pressure differential would be much smaller. The cabin might be pressurized to 8,000 feet, and outside pressure would be closer to 10,000 feet. The difference is only a few psi. At that point, opening the door becomes mechanically possible. But you'd still need to overcome the door's weight, the mechanical latches, and any electronic locks, and flight attendants are trained to prevent this. But physically, at low altitude, the door can be opened. This has happened. In rare cases, doors have been opened during taxi or shortly after takeoff, when the aircraft was still at low altitude and cabin pressure hadn't built up. In those cases, the door opened, air rushed out briefly, and the aircraft either returned to the gate or continued to a safe altitude and landed. No catastrophic failure, no explosion, just a loud noise, a pressure drop, and an emergency landing. Let's talk about the engineering of the latches themselves. Aircraft doors have multiple redundant locking mechanisms. There are mechanical latches that engage when the door is closed. There are electronic sensors that verify the door is secure. Some doors have additional pressure relief valves that prevent overpressurization. Every system is designed with the assumption that something might fail, so backups exist. If one latch fails, others hold. If the electronic system fails, mechanical systems take over. Redundancy is the core principle. Here's the real-world application. This door design isn't just for passenger aircraft. Cargo planes use the same principle. Pressurized spacecraft use it. Submarines use a version of it for hatches. Anywhere you have a pressure differential and a need for a secure seal, plug doors are the solution. They're simple, passive, and inherently safe. Now the edge case. What if there were a structural failure around the door frame? What if the frame itself cracked or the fuselage weakened? That's a different scenario. In that case, the door might fail, not because someone opened it, but because the structure supporting it failed. But that's not a door problem. That's a fuselage problem. And modern aircraft are inspected constantly to prevent exactly that kind of failure. So here's the conclusion. You cannot open an airplane door at cruising altitude. The pressure differential makes it physically impossible. If you could somehow open it, the result would be rapid decompression, not explosive destruction. The aircraft would remain flyable. Passengers would be uncomfortable and at risk from cold and low oxygen, but the plane wouldn't fall apart. And all of this assumes a scenario that can't actually happen because the door won't open in the first place. To me, that's the beauty of this design. It's passive safety. It doesn't rely on electronics or human vigilance. It relies on physics. The more dangerous the environment, the more securely the door is held in place. No moving parts, no computer. Just pressure and geometry doing exactly what they're supposed to do. And that's why, despite what movies show, opening a plane door at 35,000 feet remains firmly in the realm of fiction. Now, if you've ever wondered what actually happens when cabin pressure fails, I've covered that scenario in another video. There's one more layer worth examining: the psychological aspect. Why do people fear this scenario so much? Part of it is media representation. Movies and TV shows use door failures as plot devices because they're visually dramatic. But part of it is also a misunderstanding of how fragile aircraft actually are. People see a thin aluminum shell at 35,000 feet and assume it's delicate. It's not. Commercial aircraft fuselages are incredibly strong. They're designed to handle pressurization cycles tens of thousands of times over their operational life. Each flight involves pressurizing the cabin, holding that pressure for hours, then depressurizing. That cycle stresses the fuselage, and engineers account for it. The structure is tested far beyond normal operating conditions. There's also the concept of fail-safe design. In aviation, critical systems are designed so that when they fail in a safe direction. Door mechanisms are designed so that if a latch breaks, the door doesn't swing open. It stays closed or jams in place. If a seal degrades, it's detected during inspection before it becomes a safety issue. The entire system assumes that failures will happen and designs around them. Let's also consider the regulatory environment. Aviation authorities like the FAA and EASA have strict requirements for door design, testing, and maintenance. Doors must be tested under extreme conditions. They must withstand forces far beyond what they'd ever experience in normal operation. They must have redundant latches. They must have visual indicators showing they're properly closed. Every part of the door system is documented, inspected, and tracked throughout the aircraft's life. Now, what about intentional interference? Could someone deliberately sabotage a door to make it fail? In theory, yes, but it would require significant effort and access to the aircraft's systems. You'd need to defeat multiple safety mechanisms. You'd need tools. You'd need time unsupervised. And even then, the pressure differential would still prevent the door from opening at altitude. You'd essentially need to destroy the door frame itself, which would require explosives or extreme force. That's why aviation security focuses on preventing unauthorized access to aircraft, not just on monitoring passengers during flight. Finally, let's talk about future designs. Are there ways to make doors even safer? Some newer aircraft use electronic monitoring systems that continuously check door status and alert the cockpit if anything is abnormal. Some designs incorporate additional mechanical locks that engage automatically at certain altitudes. But fundamentally, the plug door design is so effective that there's little reason to reinvent it. It works, it's proven, and it's been keeping passengers safe for decades. So the next time you board an aircraft and you see that door close, understand what's actually happening. You're watching one of the most reliable safety systems ever designed lock into place. And once the aircraft reaches altitude and cabin pressure builds, that door becomes physically impossible to open. Not difficult, not unlikely, impossible. And that's exactly the level of certainty you want in aviation safety.